All right. All right, so you have the same factor in the numerator and the denominator is the key thing here. And if you can cancel them off, that's where your point of discontinuity exists. Okay? So this happens when you actually have the numerator is greater degree than the denominator. So if we look at this one specifically, I have x squared minus 5x plus 6 over x minus 3. If you look here, this one's degree 2, this one's degree 1. Correct? So when your numerator is greater than your denominator degree, there is a chance that you have a point of discontinuity, an open dot, an open hole. So let's look here and say, I factor that. I factor it and I get x squared, or x minus 2, x minus 3, and on the bottom I still have x minus 3. These are twins, right? Remember the x and the 3 are sewn together by the minus sign? But these are actual twins, so they would cancel off. And I would be left with this function, this f of x equals x minus 2, correct? That's a graph that's actually there. Perfect. So I go over here and I would sketch that graph. I would sketch that graph. Go away. I would sketch that graph by, this is my y-intercept. So I go to -2. And then I'm going to go up 1 over 1 and I'm going to sketch it. Boom, boom. Leave it on. And I get this line. Technically the whole line. It's drawn here. Correct? If you don't realize this, if you went to your table of values, you'll see it. 3 doesn't actually exist. X equals 3 on the table of values has an error beside it in the y value. And the reason why is, can x actually equal 3? No, it can't because of my denominator, correct? So I know x can't equal 3, but I need to find the corresponding y to figure out what the point of discontinuity would be. If they ask you for the y of the point of discontinuity, it's actually a standard of excellence question. It's the nicest standard of excellence question ever. Because all you do to find the y that doesn't exist there is you plug that 3 into the simplified equation. So here it says, to determine the point of discontinuity, substitute the x equals 3 into the simplified expression. So you put it into here. So I'm going to go 3 minus 2, so it's 1. So I know I have a point of discontinuity at 3, 1. So even though I drew it through 3, 1, I would have to go back and erase that portion. Put an open dot at 3, 1, because that means it doesn't exist there. And then draw the rest of my graph up to it. So that's how they got that graph, right? It is the x minus 2 graph, but there is that hole that we have to go put there. Okay? So sometimes we actually end up with just a point of discontinuity. When that happens when your numerator is greater degree than your denominator, because the whole denominator cancels off, correct? But if the whole denominator doesn't cancel off, we still have a denominator. Then we're going to have a vertical asymptote as well. And if we have a vertical asymptote, we have a corresponding horizontal. You never have a vertical without a horizontal. You will always have the horizontal if you have a vertical. So this one here, I was just left with this linear function, right? So I had this linear equation, I drew it, and I had an open dot. Well, it doesn't always stay that way. Let's look here. That's from yesterday. So here it says, steps to determine coordinates of the point of discontinuity algebraically. Back to the rational expression. Simplify the rational expression by canceling out factors, and substitute the NPV back in. So the first thing we're going to have to do with A is factor it, correct? Wait a second, they're the same degree. When they're the same degree, what happens? Yeah. So we can immediately, when there is the same degree, there's going to be the horizontal asymptote, and it's going to be, in this case, 1. Because it's 1 over 1, right? It's the leading coefficient. But we do need to factor it to get all the rest of the stuff. So when we factor the top, what are we taking? What are we doing to factor that? Can't do decomp product sum. What can we do? Yeah, we can do out a GCF, so we can get x and x plus 5. And then the bottom, we're going to get x plus 5 and x plus 2. Immediately when I have two factors that are the same, I have a what? A point of discontinuity. Yeah. So where is my x going to be for my point of discontinuity? Because you could just solve it out just like we did last day. Your point of discontinuity is still an NPV, correct? It's just a special one. It's the one that cancels on both. So I'm going to cancel these off. And I know that my point of discontinuity is at -5. And some people say my point of discontinuity is at -5. Is that a point? No, that's an x. So how do I get my y? You plug it back into the simplified version. So we're going to get y equals x over x plus 2 is my simplified version. So when I fill it into that, I get -5 over -5 plus 2. What does that reduce to? 5 over 3. It's -5 over -3, which is 5/3. So that's where my point of discontinuity is going to be at. Where's my vertical asymptote at? What's left in the numerator or in the denominator? What's my other NPV? That didn't cancel off. X equals what? -2. That's it. So if it cancels off, it's a point of discontinuity. If it's still, so your NPVs that cancel are a point of discontinuity. Your NPVs that stay are vertical asymptotes. That's it. So let's do our domain and range first. Asymptotes and points of discontinuity do not exist, correct? That's where the graph doesn't exist. We draw dashed lines for asymptotes. We do an open dot for point of discontinuity. Domain and range are really easy if we have our asymptotes and a point of discontinuity because it's just not those. So our domain is going to be x such that x can't equal what? What are my x's that I have problems with? -2 and -5. You have to remember the x of the point of discontinuity as well. What is my range? Y such that y can't equal what? Y is now everybody else. Here's your graph. So we need to put some sketching things on here. So I have to put a vertical asymptote, so a dashed line at x equals -2. And then I have a horizontal asymptote at y equals 1. Then what can't I forget to draw? What else do I have on there? Point of discontinuity, yeah, at -5 and 5/3. What is 5/3 as a decimal? What is it? So -5, 1, 2, 3, 4, 5, and 1.666. So it's like this. Crossed, right? How do I get more points? I could either put in x's and get out y's by plugging them in that way, or I could type the whole graph to my calculator. Type it into your calculator and go to your table of values. Remember, alpha y equals, if you have it, you type in the very original, because then at least you can't have messed it up, right? So we're always typing in our original to check it. So I have, if you do the fraction, you're going to get fraction answers, just so you know. The negative 6 and 1.5. Negative 4 and 2. Negative 3 and 3. What if I wanted negative 2.5? How would I find that? Second, trace, value, negative 2.5, and I get 5. So I have a graph running along here, not going through that open dot. Yeah, it's negative 4 and 2. That's 3. Negative 3 and 3. Wow, I'm really drawing. Yeah. Then I go on the other side, negative 1 and 1. Negative 1 and negative 1, I mean. You guys are trying B and C. Try B and C. Fill in the chart and do B and C, then we'll do the X and Y intercept. Up here, we're missing something on the range of this one. What's also missing? What also can't exist? 5 over 3. We need to have a 5 over 3 here. Because that doesn't exist on the graph, right? Good catch. Okay, so we're going to look at these whether you're done or not, just because we're going to run out of time. So here we factor the top, and we get x minus 3, x minus 4. The bottom's difference of squares, we get x minus 3, x plus 3. The minus 3's cancel, so I know x minus 3 equals 0. We did this yesterday. So x equals 3 is going to be our issue, and that's our point of discontinuity. It's going to be 3. We need to find the y value. How we find the y is we always plug it back into the simplified. If you plug it back into the original or that version you have, you're going to get 0 over 0 every time. Okay? So you have to plug it back into the simplified. So I'm going to get y equals 3 minus 4 over 3 plus 3. So it equals negative 1 over 6. So that's going to be the y of my point of discontinuity. Vertical asymptote, before I even simplify this, I can see my vertical asymptote. Sorry, my horizontal. They're degree 2, degree 2. When the top and the bottom are the same degree, you take the leading coefficients. So once again, this one is y equals 1. What is my vertical asymptote at? X equals negative 3. Because it's this one, the one that's left over, right? Now what we could do as well is we could take the leading coefficients in front of both of these x's, it's still 1. It would get you the same answer. So our domain can't equal negative 3 and 3, and our range can't equal 1 and negative 6. So we have to make sure we put both of them down. So x such that x can't equal plus or minus 3. X and out of the reals. You could have put them side by side with a comma in between. Still right. And then y such that y can't equal 1 comma negative 6. 1, 6. Y is now 0. I won't do the drawing. You can sketch it. And how do you know if your drawing's right? You look at your calculator, right? You have an open dot on your point of discontinuity. You don't forget to draw it. This one here, we have y equals 2x squared plus 5x minus 6. So we have to do decomp. So it's going to be 2x squared plus 6x minus 1x minus 3. Take out a 2x, we're left with x plus 3 minus 1, x plus 3. So our factors are 2x minus 1 and x plus 3. So my function here that's left over is a line, correct? Am I going to get any asymptotes? No. Remember this function when it's reduced, what's left over is x minus 4 over x plus 3. This is a rational function, is it not? The remainder of what's left over after I cancel, that's a rational function. So when you cancel it off, you're still left with a rational, you're going to get a vertical and horizontal asymptote. Okay? When you cancel it off and you're left with just a linear, you're just going to get a line with an open dot, a point of discontinuity. That's it. So there's two versions when you get a point of discontinuity. When they're the same degree, numerator and denominator, you're going to get point of discontinuity and a vertical and horizontal asymptote. When the numerator is a bigger degree than the denominator, it'll cancel off and you'll just be left with a line with an open dot. So you'll know what you're left with because it's whatever is left here. So I'm left with a line and then a point of discontinuity. Here I'm left with a rational and a point of discontinuity, right? It's the remainder of what's left over that tells you if you end up with asymptotes or not. So those don't exist on this one. It's just the line 2x minus 1. My point of discontinuity is at negative 3 and something. How do I find that something? I plug it into my simplified equation. So 2 times negative 3 minus 1, which is negative 7. So if I went to sketch that graph, I would just have the line 2x minus 1. So I go to negative 1. I'm just going to show you. Negative 1 is my slope. Then I rise 2 over 1. Rise 2 over 1. This is grade 10. Rise 2 over 1. Rise 2 over 1. Rise 2 over 1. Right? Then opposite to go downwards. But if I just draw this, and your calculator will look like it's just a solid line. Remember that. It doesn't really show point of discontinuity very well. If I draw this, I'm not getting full marks, because what am I missing? The point of discontinuity, which is at negative 3 and negative 7. So actually, at negative 3, negative 7, I have an open dot. And then my line butts up to it. Whereas the other ones, when you're left with a rational, you actually have a rational with asymptotes, right? And an open dot. So my domain and range are simple. Domain can't equal that, range can't equal that, right? That's all I have. I don't have any aspects. I have a line with open dot. So it's going to be x such that x can't equal negative 3. X is now really real. And then y such that y can't equal negative 7. Y is not really real. It's the same page as yesterday, but now I can actually do work. Oh, I wanted to show you one thing. So if I have this, y equals x squared plus 5x over x squared plus 7x plus 10, pay attention. If I ask you for the y-intercept, is it really easy to do? When you hear y-intercept, what should you think? X equals 0. So if I went to do y-intercept, I would go y equals 0 squared plus 5 times 0 over 0 squared plus 7 times 0 plus 10. And I would get 0 over 10, which is 0. So that's easy, and most people can do this on a test, and they'll tell me, oh, it's 0 and 0, which ends up being the same thing. But if I go this way, y equals x squared plus 5x over x squared plus 7x plus 10, and now instead of y-intercept, I ask for x-intercept. This is where people go poorly on a test. When you hear x-intercept, what should you think? So most people will do that. They'll go 0 equals x squared plus 5x. It's the next step that will tell me if I'm going to get full marks or bad marks on this test. What do I do next? You multiply up the denominator and it goes away. You're going to go x squared plus 7x plus 10. Gone here. And what's 0 times anything? 0. So it's 0 equals x squared plus 5x, which I can take a GCF out. So 0 equals x plus 5. So what are my x-intercepts at? X equals 0, and x equals negative 5, and we write them as a coordinate. 0, 0, negative 5, 0. Most people get stuck on this multiplying the denominator up and then stare at it for days. So sorry, your homework is page 451. So you're doing 4 and 5 tonight. Tomorrow we're going over transformations of radicals, which we've kind of talked about already. And how do I make an equation of a graph of a rational? Because that comes up a lot. And then Thursday we move on to other functions. Adding, subtracting, then multiplying, dividing, then compositions on Monday. Are we done?